Okay. So, turning on interaction slowly. It's not good. And that's a good. Still not ideal. Okay. Yes. So, and the idea is we turn the interaction on over an amount of time, delta t. Okay? And the idea is that if we do this gradually enough, then we can use the adiabatic theorem. What the adiabatic theorem allows us to do is to start at times far in the past here, where there's no interaction turned on. So we're in the free theory, and we know what the vacuum is there, and we know what the fields are there. And then we'll turn on the interaction, and we'll evolve those fields and states adiabatically to times where the interaction is turned on. Okay, so this means that adiabatic theorem means in the limit that this turning on time becomes very large, as delta t becomes large, and the act of turning this on happens very slowly. Just want to make sure Zach can see this. Okay. So in the limit that delta t becomes large, if we start we start in the free vacuum over here, then at late times we will end up in the interacting vacuum. So this basically is going to solve this problem for us of how to express the interacting vacuum in terms of the free vacuum. And then I can write down an explicit expression for you that says that the interacting vacuum, omega, and here we're going to work in the Schrodinger picture where the states evolve in time. Omega is then going to be given by time-ordered exponential. And I have to do this full time-ordered exponential thing here because I'm using my full Hamiltonian to evolve things, and it depends on time because of this lambda of t here. And let's say we go from t0 up to t, and we start in the free vacuum at a reference time of t0. So the adiabatic theorem tells us that if we start in an energy eigenstate, we remain in an energy eigenstate. So if we start in the state of minimum energy, we end up in the state of minimum energy. Okay? And that's how we want to define our interacting vacuum. So t0 here is some reference time in the far past. I'm just going to have to use this board here. First, I'm erasing this board. Screen is so that I don't go past it. Okay. Good. So the other thing that we can do is we can take an operator like phi, and let's consider it at the reference time t0. Okay, so at t0 we're back in the past where everything is free, and then we have a nice expression for phi, our famous expression using creation and annihilation operators, which tells us that, which is a way of writing a solution of the free Klein-Gordon equation. So just like we evolved the vacuum in the distant past up to a finite time, we can evolve this operator to any time. So at any later time, phi of t will be given by taking this free field and evolving it the way we evolve operators. Like so. Okay, that's not quite right, because again, the Hamiltonian is depending on time, and so once again, I really need to write this as a time-ordered exponential, but just for shorthand, I'm going to leave it like this, okay? Let me just say that explicitly. E to the I h t minus t0 is short for time-ordered exponential of I integral h of t. If h was time independent, this would be correct. And but in this general case, we really should write things out like that. But that's kind of messy, so I'm just not going to bother. So. Yeah, I should bother, but okay. So so now I've done what I said I wanted to do. I expressed the vacuum at any time, at later times. I expressed that in terms of the free vacuum, the interacting vacuum in terms of the free vacuum, and this is a fully interacting field here, and I've expressed it in terms of a free field there. Okay. Well, the problem is these evolution operators are very complicated, and I'm really only going to be able to get access to to get an expression for this in perturbation theory and powers of lambda. So what we're going to do now is we're going to basically try to expand this in powers of lambda, expand the vacuum in powers of lambda, get a big perturbation series, and sum it all, or well, evaluate the first few terms. Okay. Now, for small lambda, the evolution is, in fact, for lambda equals 0, the evolution is a lot simpler. It's the same as this, but we just replace h by the free Hamiltonian. That's how the field would evolve if there was no interaction. So what we really want to do is we want to perturb around the free field, so we want to perturb around this expression. We're going to expand this in powers of lambda. So we're going to write, in fact, we're going to write at finite lambda, we're going to write phi of t of x as this, plus terms of order lambda squared, and so forth. And since this is such a basic quantity, this is the leading term of our perturbative expansion, I'm going to give it a name. I'm going to call it phi sub I t0 x. I introduced that notation last time. This is called also called the interaction picture field. And it's the interaction picture operators are the operators that evolve according to the free Hamiltonian. These guys we have a nice expression for. They're just equal to this, but evaluated at an arbitrary time t. And we remember how to do that. You just replace this 3-vector inner product by a 4-vector e to the minus I arrow, 4-vector p dot x plus a p dagger to the I p dot x. So now this depends on time. This one is just a time t0. This is at an arbitrary time. Still is nicely expressed in terms of the creation and annihilation operators. And as I said, this is the leading term, the order lambda to the 0 term in our perturbation theory. So now we want the next order term. So what we want to do, actually, is we want to express this is 0. Sorry, Zach, I cut something off for you there, but there it is. Yeah. Okay. Good, so let's see. What we want to do is express the full phi of t and x in terms of this interaction picture phi. And the way it is related is what you need to do is you need to take the interaction picture guy at time t and x, and you need to undo that free evolution to bring it back to time t0. So we put just undoing the evolution by h. And we want to bring it back to time t0. And then we want to use our full formula. In other words, we want to use the full Hamiltonian to evolve it forward in time. Okay. So this undid the free evolution, and then this gave the complete interacting evolution to get us back to time t. Seems like we're going to a lot of extra trouble for nothing, but there's a nice formalism here. Okay. So I'm going to define this thing here to be call this thing here the interaction picture evolution operator, U sub I. Okay, well, actually, this is the evolution operator, that's its adjoint. And it gives us the difference between the what would have happened to phi if it just evolved freely, and what happens when it evolves with a fully interacting Hamiltonian. And you could show, and we did this last time, we sort of did it, and you're going to do it again in your homework. We showed that this is equal to the time-ordered exponential of minus I. Let me first write u out. It's e to the I, h0, t minus t0. And I want to write that out as a time-ordered exponential in its full glory. Like so. Okay, so you can show, and you will show, and we sort of showed already, that this is equal to the time-ordered exponential of something called the interaction picture Hamiltonian, where h sub I is time dependent, even if the original Hamiltonian is not time dependent, the interaction picture guy is. You take the interacting part of the Hamiltonian and you time evolve it as a Heisenberg operator would time evolve according to the free Hamiltonian. You can think of it as going to a rotating frame, rotating with the free Hamiltonian. Again, Zach won't be able to see that, so here you go, Zach. Okay. And let's see. Let me actually say what the interaction picture guide is for our particular case. Okay. So it's equal to free Hamiltonian evolution, and we write down explicitly our interaction term. And then minus I H for this phi is supposed to be evaluated at time t. Okay, so what you got here then is integral d3x lambda over 4 factorial, and then you can write this as e to the I h0 t minus t0 phi. It should be the fourth power. Okay, and I've inserted some factors of e to the IH0 times e to the minus IH0 in here. Okay, standard trick. And this here is nothing but, where's that? This is nothing but the interaction picture field here. So that's really nice, actually. It means the interaction picture Hamiltonian, you can write just directly in terms of the interaction picture fields. Just replace the usual fields by the interaction picture fields. Okay. So let me write down our yes. This is our result actually that relates phi. Where's the result? Phi of x to the interaction picture fields, which are the simple guys. So phi at time t is equal to u sub I dagger e to 0 phi sub I dx u sub I t to 0. Where u sub I is written, is the time-ordered exponential of this interaction Hamiltonian, which is expressed entirely in terms of the interaction picture fields, which just involve creation and annihilation operators. So I'm going to make that even more explicit. I'm going to write that as 2xi of integral of lambda over 4 factorial phi of prime x dt prime. That's the interaction picture phi raised to the 4th power. times phi interaction times time-ordered exponential minus I. Same thing. Fourth power. Yeah. Sorry, I forgot. There's also, of course, there's an integral over d3x as well. So there's an integral of t prime and a d3x, and the same thing. Okay. It's not beautiful, but it is what we were looking for. Each of these, phi i's, we express in terms of a's and a daggers. Okay? We can expand these time-ordered exponentials out in powers of lambda. Maybe I'll make that even more explicit, okay? So this is 1 plus I write d4x here, plus phi, put the lambda out in front here. Write that as phi, so I of t prime of x d4x. Plus the next term is I lambda over 4 factorial squared. Double integral. Yeah, t prime there. This is the time-ordered product, so we make sure that we have arranged these operators so that later times are on the left. And this is a d, well, there's a d3x and a d3x prime, and a d, let's call this x double prime. And a d4x prime and a d4x double. Are people clear what's going on here? Because this is getting, the notation is getting kind of out of hand. Simply, it's because I wanted to expand things explicitly for you, to tell you a little bit more about where we're going. Okay, so that would be the expansion of this time-ordered exponential here. Okay? What I did here was I made sure that t prime was always greater than t double prime. T double prime is what we're integrating over in this second integral here. And so it only gets integrated up to t prime. So that guarantees t double prime is less than t prime. Okay, so that's the explicit expansion of this first guy. Then we multiply by the operator. This doesn't just have to be the field phi, it could be any operator of x. And then we have another expression. I won't write the whole thing out, just the first term. Oh, nobody copied. This is to the fourth. Okay. Beautiful. Absolutely beautiful, isn't it? Okay. The point of writing all this out was now you can see how it's really just an expansion in powers of lambda. I can multiply all this out and get an order lambda, an order lambda squared, and so forth. A systematic expansion, a systematic perturbation theory to get the interacting field in terms of the free field. Everything will, in the end, reduce to creation and annihilation operators. Gosh. Between the fire drill and getting late, started late because of the video, we're not getting through very much. So maybe we could continue at 1 o'clock if it's okay with everybody. Just let us know. If you're not done with your meeting by then, can you somehow get us a message and we'll send an email? Okay. And we'll figure something out. Would you normally be done by 1 o'clock with this meeting? Yeah. Okay. Let's assume that it works. But if not, then we'll just postpone. Okay. Because yeah, let's see. Because you had a lab at 2:30, right? Yes. Okay. Let's see if there's anything else I want to tell you before, while I've got all these equations up on the board. I'll just say one more thing. Okay, so I defined this U operator, evolution in the interaction picture, always starting at time t0, but it's going to be useful for us to have an operator that goes between any two times. And that's going to be, the appropriate operator is between t and any prime t prime, not just our reference time t0. It's going to have this form. Should be, sorry, this is, yeah. Okay, so if t prime is equal to t0, then this factor here is 1, and it reduces to the expression we had previously. But more generally, if you want to evolve between any time t prime and a time t, what you got to do is you have to first translate yourself from t prime back to t0, which is our reference time at which the fields are free. Then you evolve with a full Hamiltonian, and then you undo that, or you put back in the H0 evolution to bring it back up to time t. And so we're going to use this actually to evolve operators not just from t0 to t, but between arbitrary times. It's clear from this expression that u sub I is unitary. U sub I dagger times u sub I is the identity. That's because this is a unitary operator, that's a unitary operator as you show in your homework, and that's unitary. And it also satisfies these composition laws. That if you evolve time 3 to time 2 and time 2 to time 1, that's the same as evolving time 3 to 3 to T1. And so forth, other nice properties. So let's take a break now, and we will, when we come back, we will talk about, we talked about how to write the interacting field in terms of free field operators. Now we want to see how to write the interacting vacuum in terms of the free vacuum. And once we do that, we'll put all the ingredients together and find an expression for a correlation function, a general correlation function. Okay, that's all for now. Yes. Huh? Yeah.
What's this T
T, that's time-ordered exponential. And that's something you, in general, when you're dealing with a time-dependent Hamiltonian,